So the idea of related rates is that you are trying to see how variables are changing with respect to time or with respect to each other. It doesn't always have to be time. But it makes use of the principles of implicit differentiation because, or rather, instead of just using y prime, you're differentiating with respect to both. And you'll see that more in the examples that I do. So when you're solving a problem, I have it written in all caps here, always draw a picture because they're always going to be something that is geometric of some sort. So like water is flowing into a cone at a rate of, I don't know, 3 meters cubed per second or something like that. That's a lot of water. But you have to know like what's actually happening with these geometrical shapes in order to understand how to solve the problem. So always draw a picture. This will also help you with variables because you usually have to distinguish what variable is which, and therefore the name of whatever you're differentiating. So if you were doing area, it makes sense to do, this is with respect to time, it would make sense to do dA dt because you're doing area and time. So after that, write down what rates are given to you. And it could just be 1, but usually with the simpler problems it's going to be 2. As it gets more complicated, it might just be 1. And usually the units will be really helpful in determining what you're given, because you may say, oh, okay, so the size of this cube is, or each edge of this cube is expanding at a rate of 2 meters per second. What does that even mean? Well, you're given meters per second, so that's going to be distance over time. And you could say, since it's an edge, you can do a lowercase a, that is, dA dt. And after that, you're going to write down what you're trying to solve for. And again, the units will be really helpful in determining this. And after that, you can just solve the equation. So my teacher taught me a really simple way of doing this that's called bar.bar. And as you can see, it's because you have a bar and then a dot, which would be multiplication, and then another bar. And that's just to say that you're doing 2 fractions. And let's see, I have example problems further down here. But as you can see, given area with respect to time, and you need to find I don't know, one of these, then you can say that dA over dt is equal to dA times ds dt. And if this was, say, 1/2 times 2 over 1, the 2's would cancel because it's the same variable. And that's the whole principle of bar.bar. So if you were given something like this, it would be easy to fill in whatever variable you're missing, and the problems will always have it so that it should fill out equally. So here's an example problem, because I know that makes very little sense at the moment. So if we are given a cube, which I'm trying to get on screen, with edges increasing at a rate of 6 centimeters per second, how fast is the volume increasing when an edge length is 2 centimeters? So we are given dx dt, as you can see, with the distance and the time, saying that x would be the edge length, and that is 6 centimeters per second. And what you want is the volume with respect to time at this certain point. So for bar.bar, that would be volume, which is what you want, over time, is equal to the volume with respect to x times x with respect to time. So, given the volume of a cube, which would be the edge length squared, or cubed, my apologies, if you differentiate that, that would just be 3x squared. And so if that is when x equals 2, as we see in the problem here, you just substitute in 2. 2 squared is, of course, 4. 4 times 3 is 12. And so that gives you dv dx. And you can just substitute that right into the equation and say dv dx is 12, and we are already given dx dt, which is 6, so 12 times 6 is 72 centimeters cubed per second. And the units are very important when you're writing your answer because it will help you see if you actually did your answer correctly. So moving on to a little bit more complicated of a problem. I'm not going to spend too much time on this because I would like to do a practice problem from the exam. we are given water is pouring into a cone at a height of h and a diameter of 3h at a rate of 10 feet cubed per minute. At what rate is the height changing when the height is 15 feet? So this is actually, I have a practice problem workbook that is called 3000 Solved Calculus Problems, and it's very, very helpful, and it just gives you a bunch of problems and it has them solved. So here is me solving this problem. So if you're wondering why it's phrased like this, it's from the book. Don't blame me. I've drawn this little cone here, and it has the water going in, and this cone is filling up. This height is h, and the diameter is, of course, 3h. And as we can see from the problem, we're giving the volume with respect to time, which is 10, and you want the height with respect to time. So our bar would be dh dt this time is equal to dh over dv times dv over dt. And we know that the volume of a cone is pi r squared h over 3. So if you remember that r, sorry, I know it goes back and forth, but it makes sense. So r in this case is half of the diameter, which is 3h. So you could say that r is equal to 3 over 2h, which is what is substituted in here, because it's easier just to have that one variable instead of r and h, and because the two are related, we are able to do this. So then simplifying that out, we simply get 3 pi h cubed over 4, and then we can just substitute in 4h. My apologies, that is not what we're going to do. We see that we have gotten dv dh, but if we go back to our bar, which is over here, we see that we need dh dv. So it's pretty simple. You just flip it, and then you would get 4 over 9 pi h squared. And then you can substitute in to the equation as I was trying to do just now. And just multiply it out, and you should get some really strange number. So now we're going to do a problem from the exam, or one of the practice exams. So we are given that all edges of a cube are expanding at a rate of 2 centimeters per second. How fast is the surface area changing when each edge is 3 centimeters? So I'm going to draw my cube, and it's not going to be the most beautiful cube ever, but it's okay. It doesn't have to be perfect. Don't have time for perfect. And I'm going to say that this edge length is A. So from the problem, we are given dA dt, and that is 2 centimeters per second. And we want ds dt, which is the surface area with respect to time, as we can see right here. And this is when A is equal to 3. So we know that the surface area of a cube is equal to 6a squared. And I'm going to use implicit differentiation in this case, since I already showed you bar dot bar. And this could be considered simpler to some other people. So we're going to differentiate the surface area, and that would be ds dt. We're going to differentiate this implicitly. And on this side, it would be 12a dA dt. And so we know that we've already got dA dt, and we also know a, so you can just go ahead and substitute both of those in. This is a very simple problem. And then that would be 2, and then you have 6 times 12 is, of course, 72. And then for our units, be centimeters per second. And there you go.